Hello and hi everyone. We are from C3 Group 31 and today we will present our integrated design project. So I'll pass to the first presenter.
Hi, my name is Ridwan Shahmi bin Ismail and I will present to you the introduction to our integrated design project. First of all, methanol is the simplest alcohol with only one methyl group and one hydroxyl group. It has a boiling and freezing point of 64.9 degrees Celsius and negative 93.9 degrees Celsius at 1 atm respectively. Methanol has partially negative hydroxyl group and short carbon chain, making it a polar molecule. Physical properties of methanol are light, colorless, volatile, flammable and toxic, and has a distinctive odor. Next, we will explain and propose suitable plant capacity of methanol production by analyzing local market in Malaysia. Sarawak Petchem, one of the biggest methanol production in Malaysia, produces 1.7 million tons of methanol per year, which is about 4,657.3 tons per day from the natural gas feedstock supplied by Petronas. Therefore, in our opinion, the suitable capacity for the plant production is 4,800 tons per day. Next, lastly, I will explain on selection of instrument for methanol production process. First of all is reforming reactor. Second is condenser. Third is methanol reactor. Fourth is syngas recovery unit. And lastly, methanol purification unit. That is all from me. I will pass to the next presenter.
Hi, my name is Nurul Ashkin and I'll be presenting Chapter 2 Part 1, which is the process flow diagram. This is the overall diagram of the methanol purification process. Firstly, the water liquid is heated to water vapor at 210 degrees Celsius. Then in the mixer, methane vapor, which is stream 1, and water vapor, which is stream 2, are mixed together and it is preheated to 450 degrees Celsius before entering the reforming reactor. In reforming reactor, the steam reforming occurs in which a mixture of carbon monoxide, carbon dioxide and hydrogen gas are produced, and this is the equation of chemical reactions occurred. Then the product of reforming reactor, which is stream 3, is fed into a condenser in order to remove 95% of the excess water through the bottom stream, which is stream 4. Next, in the methanol reactor, the syngas undergo hydrogenation process to form methanol vapor. And this is the summary of those chemical reactions. The optimum temperature for those reactions to occur is in between 200 to 350 degrees Celsius, while the pressure is in between 50 to 150 bar with the presence of copper as a catalyst. Next is syngas recovery unit. This is used to separate methanol from the excess syngas. Here, the bottom products, which is stream 10, which consists of methanol and water, is fed into methanol purification unit, while methane, carbon dioxide, carbon monoxide and hydrogen gas is recovered as the overhead products, which is stream 7. This stream is then split into two. The first one, which is stream 9, is being purged, while the other one is stream 8 is recycled back to methanol reactor. The last one is methanol purification unit, which is a distillation column. Here, the excess water is removed to obtain the pure methanol. The overhead products, which is stream 11, is the vapor mixture of methanol, and this stream is being split into two streams. The first one is being refluxed back to methanol purification unit, while the other one is collected as the final product. Then the bottom products, which is stream 12, is the liquid mixture of methanol with 95%. This stream is also being split into two. The first one is removed as a wastewater to the wastewater treatment plant, while the other stream is returned back to methanol purification unit.
Hi, my name is Michelle and I'm going to present about Chapter 2, Part 2, which is the material balance of the process. So our material balance calculation is start from the methanol purification unit. So based on the market analysis, we know that the mass flow of the stream 11 is equals to 4,800 tons per day. And there are a few given information from the problem statement, which is the methanol need to be 95% purities and a fraction of the feed that is vaporized in the distillate S11 is 0.93. So after performing all the calculation here, we can get that the mass flow for the S10 and for the S11, the mass flow is got from the market analysis, and the S12. After that, we can continue our calculation in the syngas recovery unit. So after performing all the calculation, we can get that the mass flow for the stream 6 is equals to 22,332.64 tons per day, and the mass flow of the stream 7 is equal to 17,171.35 tons per day. So in the splitter, in order to achieve the material balance at the methanol reactor, we assume that the string only contains the carbon monoxide, the carbon dioxide, and the hydrogens. After that, in the methanol reactor, the extension of the reaction method is used to calculate the reactive material balance. So in a splitter, we can get the molar flow rate of the string line with all the mole fractions of each component from the calculation, and proceed our material balance to the condenser by performing the material balance. So we can get that the mole fractions, the molar flow rate of the string is. After that, in the reforming reactor, by performing all the material balance calculations, we can get the molar flow rate of string 1 to string 4. So the conclusion for the whole material balance is that at 1,807.78 kgmol per hour of the methane and 13,174.96 kgmol per hour of the water is needed to supply to the plant in order to produce 4,800 tons per day of the methanol with 95% purity.
Hi, I am Masdena. I would like to present Chapter 3, which is Chemical Engineering Thermodynamics 2. For question 1, we are required to generate the VLE equilibrium graph from the software. VLE is used to describe the composition of mixture in saturated vapor liquid phase. The VLE represented by two graphs, which is XY and PXY diagram. By using Aspen HYSYS, the VLE of the graph XY and PXY diagram give better understanding on the mixture composition in liquid and vapor. So this is the XY diagram. The blue line represents the vapor composition and the red line represents the liquid composition. The liquid and vapor composition are always in equilibrium. This is the PXY diagram at temperature 58 degrees Celsius. The blue line represents the bubble point and the red line represents the dew point. The region between bubble and dew point is the saturated mixture phase. After analyzing the graph between HYSYS and our reference from DDBST website, we can conclude that in PXY and XY diagram, change in both equilibrium lines are small, although the data from DDBST website and HYSYS are from different temperature. For question 2, we are required to generate the phase envelope of the mixture. So this is the PT diagram. The PT diagram generated by both bubble and dew point of the mixture is same as figure shown below, as the methanol and water are isotrope. Next, this is the PV diagram generated by the HYSYS. For question 3, we are required to do the flash calculation. Peng-Robinson-Quibie equation of state was utilized in this simulation as the mixture is polar and contain liquid. The mass flow rate of S3 is assumed to be 100 kg per hour. Based on reference, we set 900 degrees Celsius and pressure at 21 bar for the inlet of S3. The outlet of S3 being separated into S4 and S5. The main condition of S4 is 90% of water being removed. S4 is the liquid stream with molar flow 10.83 kg/mol per hour. S5 is the vapor stream. By flash calculation generated by HYSYS, the vapor composition and liquid composition in S3 is shown at the table below.
Hi, my name is Michelle and I'm going to present about the chapter 4. So this chapter is emphasized on the methanol purification unit, where the methanol water mixture is separated by using multi-stage and counter-current distillations. So from the diagram, we can see that the S10 will be the feed stream, the S11 will be the distillate, and the S12 is the bottle stream. The vapor stream of the distillation column has been cooled down in the condenser and converted into the liquid. And the part of the liquid is returned back to the distillation column as a reflux, or the remaining product is methanol. Then the reboiler also implemented in this plant, where the liquid stream from the distillation column has been partially boiled up to produce vapor liquid mixture. The vapor stream has been returned back to the distillation column, while the remaining liquid consists most of the water will be discharged into the wastewater treatment. The installation of the condenser and the partial reboiler is to ensure that the distillation column be able to operate counter-currently. So for the mass flow rate of the S10 that we obtain from the material balance in chapter 2, we convert into the molar flow rate by using HYSYS software. And the mass fraction of each component in each stream are also converted into the mole fractions. So the assumption that we have made in this part is that the mixture of the water and methanol is an ideal binary mixture. The system obeys Raoult's law, where the vapor forms an ideal gas at low to moderate pressure and the liquids form an ideal solution with chemically similar species. So these are the sample calculation to calculate the mole fraction of the component in the S10. And after we have the mole fraction of the component, we can calculate to the molar flow rate of string 11 and string 12 by performing the material balance. So these are the steps of determining the number of trays in the graph. So the method we use is the MC-cap tau method. So for the first step, to plot the equilibrium line, we need to substitute the value of the XA into this equation, then we can get the value of YA. So with this data, we are able to plot the equilibrium curve on the graph. After that, we need to determine the Q line. So by using the formula Q equal to 1 minus F, where the F is given in a problem statement, which is 0.93, we are able to get the value of Q, and we substitute back into the equation for Q line, and we are able to construct the Q line on the graph. After that, to find the minimum reflux ratio, so from the graph, the intersection point is obtained between the equilibrium curve and the Q line. By substituting these two values into the formula, we can get that the R min equals to 0.1. So after that, we need to determine for the optimal reflux ratio. So according to literature, we already know that the optimal reflux ratio is between the range of 1.2 R min to 1.5 R min. So therefore, by comparing the R1 equals to 1.2 R min and with R2 equals to 1.5 R min, the optimal reflux ratio can be determined. So we just need to substitute the R min value into the R1 equation and R2 equation. We can get that the R1 equals to 0.12 and R2 equals to 0.15. So for trial 1, we need to substitute the value of the R1 into the equation and get the R1 operating line. And for trial 2, we need to substitute the value of the R2 into the equation and get for the R2 operating line. So by plotting these two operating lines into two different graphs, we can determine the number of stages. So after plotting the graph, we can see that for the trial 1, the number of trays needed is 2.13 plus 1 rebroiler, and for the trial 2, the number of trays needed is 1.13 plus 1 rebroiler. So from the result, we can see that the number of trays that required for the trial 1 is for the trial 2 is lesser. So for the R equals to 1.2 R min, which is the trial 1, the number of trays required is 2.23, while for the R equals to 1.5 R min, which is the trial 2, the number of trays required is 1.93, which is lesser. So therefore, in order to reduce the operating cost, the optimal reflux ratio is 0.15, which is the trial 2, which only results in 1.13 trays. So to conclude, in order to achieve 95% parity of the methanol production, the number of the trays required in this distillation column is 2. So that's all for group 31. Thank you.